Last time we started section 3.2, we covered the product rule, which tells us how to take the derivative of a function that is in the form of a product. And today we're going to finish the section by looking at the quotient rule. So here we'll be looking at a function that is defined by a quotient of two functions of x, and we'll learn the rule for how to take the derivative of that type of function. We're going to derive the quotient rule using the same approach we did to derive the product rule. We're looking at a function that's in the form a function of x divided by another function of x. So let me write what we're looking at is y equals some function f of x divided by another function g of x. So we're going to define u to be the numerator function and define v to be the denominator function. And in order to get to the derivative, we know we need to look at how much things change. So if we let x change by some amount delta x, that causes u and v to also change because u and v are functions of x. So the amount that u changes we call delta u, the amount that v changes we call delta v. So now we want to calculate how much does the quotient change. So what we do is we take the ending value of the quotient after u and v have both changed, minus the beginning value of the quotient, which was just u over v. Then we simplify by getting a common denominator, where we just multiply the two denominators. So in this fraction, we need to multiply by v over v. So you can see the numerator here has been multiplied by v. And on the second fraction, we need to multiply by this expression, v plus delta v, over the same thing. And so you can see here we take the u and multiply it by v plus delta v. Then you can distribute, and notice the first term here is uv, and over here when we distribute we have a negative uv, so those two terms cancel. So all that's left is v delta u, and then the minus distributes, or minus u distributes, becomes minus u delta v. Okay, so we'll keep working with this on the next slide. This is the formula where we left off. Now we're going to go from an incremental change in u over v to finding the derivative, which is no longer over an interval, it's now at a single instant. So the derivative of u over v, we know we take our delta of our function over delta x, that's like the slope of the secant, and then we take the limit of that as the increment goes to 0, right? This is just following the limit definition of the derivative, but the function we're taking the derivative is u over v. Now we can plug in the formula up here for the numerator. And so we keep our limit sign. Now over here we've done a little rearranging. So we took this over delta x. We kept the denominator here. And then the delta x, instead of writing it in the denominator, we pulled it up and applied it to each of the terms in the numerator. So you can see there's a delta x, there's a delta x. Now we're ready to take the limit. So in the we can split the limit up to each term as long as all those limits exist. On the first one, we're taking the limit of this product. The v doesn't have a delta x in it. So the v can be pulled in front of the limit, which we did here, and that leaves limit of the other term. Similar here, the u doesn't have a delta x, so it can be pulled in front of the limit. And then in the denominator, again, this v can be pulled out in front of the limit. Now this limit is exactly the definition of the derivative of the function u with respect to x. So that limit can be replaced with du dx. Right, that's the notation for the derivative of u with respect to x, and there's still this v in front of it. Similar over here, this limit is the definition of the derivative of v with respect to x, so we call that dv dx, and there's a minus u in front of it. Now in the denominator, as we let delta x go to 0, that means the amount that x is changing goes to 0. Well, since v is changing as a result of delta x, if we let delta x go to 0, that means the change in v is also going to go to 0. So if this goes to 0, we're left with the limit of v, which v is like a constant because there's no delta x in it. So the limit of v is just v, and then it's multiplied by another v in front. That becomes v squared. So this is our derivation for the quotient rule. It tells you how to take the derivative of this quotient type form. We'll formalize this on the next slide. So I wanted to show the derivation just so you'll see where it came from. You don't have to use this again. We're just going to ask you, you're not going to need to reproduce the derivation. You'll just need to be able to use this rule, which we'll do a lot of practice with. This is the formula we just derived for the derivative of a quotient, u over v. Here we write it in our formal version. Here we've made the substitutions. If you recall, we defined u to be f of x, v to be g of x, so we've put those back in. And then we've just made that change, all those substitutions everywhere here. Now this looks really complicated, but we'll go through an easy way of thinking about this. So one way that might make this easier to look at is to leave off all the parentheses x's after each function. And we could switch, if you wanted, to the prime notation. So we're taking the derivative of this quotient f over g. On the right we have a fraction. In the numerator we have g times the derivative of f, so that's f prime, minus f times the derivative of g, so g prime, and the denominator is g squared. So the way that we often say this in words that helps make this easier to remember, I'll just refer to numerator as top and denominator as bottom. So over here we have bottom times the derivative of the top minus top times derivative of the bottom, and then in the denominator we have bottom squared. So it's important you remember which one is the plus and which is the minus. So you don't want to reverse it, right? It would be wrong to say top times derivative of the bottom minus bottom times derivative of the top. You have to get it this way. It's always bottom times derivative of the top minus top times derivative of the bottom. In this example, we're asked to find the derivative of the given function. So when you look at this function, you see it's a quotient, and both the numerator and denominator are functions of x. Right? If the denominator were, say, a constant, then you don't really have to view this as a quotient, and we'll talk more about that later. But here it's clearly a function of x over a function of x. So let's just go through the common mistake, right? So it would be wrong to think you could find this derivative just by saying derivative of the top, I'll just use the prime notation, over the derivative of the bottom. Right? We had the same thing with a product. With a product, you can't just take the derivative of each factor individually. We showed that didn't work. Same thing with a quotient, right? The quotient rule tells us this is not the way to do it. Right? So if you continued in this way, in the top you'd carry along the 2, and then the derivative of e to the x is e to the x. In the denominator we'd use the power rule. You'd get 3x squared minus 0. Okay, but that is wrong, so we're not going to use that. So here's the correct solution. So to find f prime, we know we're going to use the quotient rule. So the result will be a quotient. The denominator is easy. We can fill that in. You take the original denominator and you just square it. So make sure you put parentheses so the whole thing is squared. Okay, now the numerator, you start with bottom as it is times derivative of the top. I'll go back to the Leibniz notation here. So derivative with respect to x of the top. Then you continue on and you say minus top as it is multiplied by derivative of the bottom. Okay, we're not done yet because there's still some derivatives to compute. So let's continue on. I'm going to just leave the denominator as it is. I don't see any reason to square that out. Now in the numerator, we keep the first term. And now we need to compute the derivative of 2e to the x. So when we've got that constant 2 multiplied by, we just carry that along. And then the derivative of e to the x is e to the x. Continuing on, we have minus 2e to the x. Now we find the derivative of the next expression, so that's 3x squared minus 0. Okay, so technically we're done. This would look nicer if we simplified it a little bit, so maybe we'll do that just to be complete. But the new part is done, right? The rest is just algebra. So distributing over the parentheses, we're going to get 2x cubed e to the x minus 8 e to the x. And then the next product is minus 6 x squared e to the x. And there's no like terms to combine, so that's probably as far as I would take that. You could factor out an e to the x because that's common to all three terms in the numerator, but this version is fine also for simplifying. Okay, so this was our first example of the quotient rule. So the first thing is you have to recognize that you had to use the rule, and that's because we had a function of x over a function of x. So we know we can't just do what our intuition might tell us, which is take the derivatives individually. It doesn't work. So using the quotient rule, we knew that was the rule. Plug in all the pieces, so bottom times derivative of the top minus top times derivative of the bottom over bottom squared. And then we had these two derivatives to compute and simplify. Got a couple more examples here to compute the derivative. So in number 1, notice we've got a fraction. The numerator and denominator are both functions of t. Right, so now t is our independent variable instead of x. So we have to use the quotient rule on a problem like this. So we could say y prime for the derivative, or to be a little more complete, we could use the Leibniz notation. Now because it's a function of t, we don't want to call it dy dx, we need to call it dy dt. Now applying the quotient rule, let's go ahead and put in our denominator. So we take the original denominator and square the whole thing. Now in the numerator, we take bottom as it is, multiplied by the derivative of the top. Now that's the square root of t. We've seen this before. To make it easier to take the derivative of the square root function, it helps to rewrite the square root of t as t to the 1/2 before you take the derivative. Then we have, so that's bottom times derivative of the top, minus top as it is, times derivative of the bottom. So the next step, we'll compute these derivatives. So we keep our denominator the same. In the numerator, the first part, we don't need to do anything. And then we get to this derivative. So this is t, variable t to a constant power. We use the power rule to find its derivative. So we bring the 1/2 down in front, and we reduce the power by 1. And the current power is 1/2, so when you subtract 1 from that, you get negative 1/2. Then we've got minus square root of t. Now we compute this other derivative, so using the power rule, we get 2t plus, and then we've seen that the derivative of a constant times t is just that constant. Okay, and you could simplify, but I'm not going to take the time to do that. That's not the new stuff we're learning. And on a test, I'd be fine if you left it like this. Okay, let's go to number 2. So we see a quotient here, and you could use the quotient rule to find this derivative. But you don't have to. You can save yourself a lot of work if you notice the denominator is a constant. You really only have to use the quotient rule if it's a variable expression in both the numerator and denominator. Or, yeah, I guess that sometimes if it's constant in the numerator, you still may have to use the quotient rule. But if it's a constant in the denominator, the easy way around this is to first rewrite y so it's not even looking like a quotient. So I could pull out the 2 over 3 and write it as 2/3 times x to the 5th. This is just like a constant times x to a power, so to find its derivative, just use the power rule. Okay, so now we don't even need the quotient rule. The quotient rule is kind of a long one, right? So it's easier if you can avoid it. And this is one case where we can avoid it. So then I'm going to write for the derivative, since y is a function of x, dy dx equals, now we just keep the constant, right? If it's multiplied by a constant, you just carry that along. And then we multiply that by the derivative of x to the 5th, which is 5x to the 4th. And then simplifying this, we get 10 over 3 x to the 4th, and you can see how easy it was to find this derivative by avoiding the quotient rule. Like I said, it would have been fine to use the quotient rule, and you would get to the same answer. It would just be a little bit more work to get there. So if you want to test that yourself, it'd be good practice with using the quotient rule, and you can see, hopefully you can get to this same result. So this is pretty much the end of this section on the product and quotient rules. At the end of the section, if you check in your book, you'll see this table, and it summarizes the rules we've learned so far. And these are all the shortcut rules, right? These help us take derivatives of functions without having to use the limit definition of the derivative. So let's quickly go through these. So we saw the derivative of any constant is always 0. Over here we have the power rule, right? It applies if you have a variable x raised to a constant power. We learn the derivative of e to the x equals itself. This is the constant multiple rule. If the function you're taking the derivative of is a constant times some expression of x, you can pull out the constant, just carry it along, and then just take the derivative of the other part, the function of x beside the constant. This is the sum rule. You can take the derivative of each term separately when you're dealing with a sum. Same thing with the difference. You can just take the difference of each one separately. It's the product and quotient where you can't do that, right? So to take the derivative of f times g, it's not f prime times g prime. You can't just apply the prime to each term. So instead, we have this formula we call the product rule. For a quotient, same thing. To take the derivative of f over g, it's not f prime over g prime. It's this other formula that we derived as the quotient rule. We're continuing in Chapter 3, where we're learning differentiation rules. In the first 2 sections, we learn shortcuts for taking the derivatives of certain kinds of functions. So we've learned how to take derivatives of polynomial functions, and also the exponential function e to the x, and then functions that are in the form of a product or quotient. In this section, we're going to learn shortcuts for finding the derivatives of all 6 of the trigonometric functions. Let's start by looking at the sine function. One thing I want to mention before we even get into this at all, for all the trig functions, you've learned in trig that the input can be thought of as an angle, and that angle could be either in degrees or radians. But in calculus, it's pretty much always radians. So when we're taking derivatives and so on of our trig functions, they'll always be in radians. So the x here represents the angle. It's in units of radians. So our goal first is to find the derivative of the sine of x function. So first, let's just think about it graphically. So here I'm shown a graph of the sine function that we're all familiar with, right? It has period 2 pi. And let's use the methods we've already learned about taking a graph of a function f and figuring out what the graph of f prime would look like. So for example, some easy points to work with are points where we have a horizontal tangent. So notice at x value pi halves, we're here, we have a horizontal tangent, which means the f prime value is 0 because the slope of that is 0. So down here we have a 0. There's another one here at 3 pi halves, slope 0, so the function value for f prime is 0. And we have two others that we can see that are the same. Now let's look in between these two horizontal tangents. So any point on this part of the curve the tangent has a positive slope. So the y prime will have positive values, right up above the axis, positive. And then between pi halves and 3 pi halves, if you pick any point here, the tangent is decreasing, has a negative slope. So on the corresponding part of the curve, this x interval here, all the y values for f prime will be negative. And you can do this for all of this graph, and you produce the red graph down here. Now this graph looks like the cosine function, right? Remember, sine starts at 0, 0, and then it goes up, starts its wave. Cosine starts at 0, 1, and starts by going down to create its wave. So this looks like the cosine function. And this is, our starting graph was sine, and we graphed the derivative of sine, and it looks like cosine. So our guess, based on this analysis, is that the derivative of sine is equal to cosine. We're going to investigate this now using the precise definition and see if this guess is correct. Now we're going to use the actual definition of the derivative to find out for sure what the derivative of the sine function is. So we'll define f of x to be our starting function, the sine function. And then right here we have the definition of f prime of x, right, our limit definition. Making the substitution, f of x plus h would be sine of x plus h. Got that here. And then minus f of x is just sine x. So in the next step, we're going to use a trig identity for sine of a sum. So you would have seen this in your pre-calculus class. So you don't need to have that memorized, but I'll just remind you what it said. So sine of a sum is equal to sine of the first times cosine of the second, which is here, sine x cosine h, plus cosine of the first times sine of the second, right? So x is first, h is second. So just to add some brackets here, this part came from using the trig identity on this part. So then you can see there's still a minus sine x that we need to keep in the numerator. So that was the only change from this line to this line. Now in the next line, we've got this fraction with a sum or difference of 3 things in the numerator. We're going to put the first and the third, we're going to keep that here, and then we're going to pull out this second one and write it as a separate fraction over the same denominator. Okay, now using a limit law, before we get to the limit law, we're just going to, on this first fraction, we can factor out sine x, and that leaves cosine of h minus 1 after you factor that out, and we still have the over h. And on the second term, we just pull this cosine x out in front. That leaves sine h in the numerator, still have h in the denominator. Now we're ready for our limit laws. So we have limit of a sum. We can split the limit up to each term separately. And we've done two things. Also, the limit of this first term, because our limit is involving h, right? H is the thing that's approaching 0. Sine x doesn't have any h in it. So in terms of the limit, sine x is like a constant. So it can be pulled out in front of the limit sign. Or actually, they got there in the same way. Sorry, let me rephrase that. So we have limit of a product. So you can just say limit of the first times limit of the second, which is here. And we do the same thing here, limit of a product, so limit of the first times limit of the second. And then what I was saying a minute ago, because there's no h in sine x, it's like taking the limit of a constant. So the limit would just be that constant. Now this other limit is not obvious. It turns out to be 0. I'll come back to that in a second. Here, same thing. The limit is involving h, but there's no h in cosine x. So it's like taking the limit of a constant, which would just be that constant. And we have another limit that's not obvious, but it turns out to be 1. So let me just mention those two limits now that were not obvious. So one of them was limit as h goes to 0 of cosine h minus 1 over h. If you try direct substitution, you get a 0 in the denominator, so we know that's not going to work. So here you could just guess this limit by how we first approached limits, by taking numbers for h and let them create a table of values for h and let them get closer and closer to 0. So you might start with h equal to 1 and then go to 0.5, then or maybe 0.1, 0.01, 0.001, and create a table of x, y, or actually h values, and then the y would be these values with the corresponding h. And then look at the table and see what this is approaching. And you'll see that those terms are getting closer and closer to 0, so that turns out to be 0. And then the other one, you could do a similar approach. We had limit as h goes to 0 of sine h over h. Just create a table of values and you'll see that these get closer and closer to 1 as you choose h is closer and closer to 0. So we didn't prove these, but if you created tables, you could convince yourself that these limits are correct. And then final simplification. This times 0, that whole term disappears, plus cosine x times 1, so it's just cosine x. And that's what we got using the limit definition of the derivative of the function sine x. So our conclusion over on the right is that the derivative of sine x equals cosine x. And that's exactly what we guessed on the previous slide, just based on the graph. And here we proved that it is correct, that the derivative of sine is cosine. So we're asked to find the derivative of the given function. So the first thing you have to notice is that this is a product, because we have in parentheses a function of x multiplied by another function of x. So we don't want to make the mistake of just taking the derivatives of each individual term. It doesn't work that way with products. Okay, so this is a product. So that tells us we need to use the product rule. So what we're seeing is that we often combine rules, right? At some point we're going to have to use the rule we just learned for the derivative of sine, but we're not ready for that yet, right? The bigger picture is we have a product. We have to deal with that first. Okay, so f prime of x equals, start with the product rule. So remember, it's first times derivative of the second plus second times derivative of the first. Now we have some derivatives to do, so on our next line we keep the first expression. And then we just learned the derivative of sine x is cosine x. Then we have plus, keep the sine x. Now we need the derivative of x cubed plus 1, which is we know earlier how to do that kind of derivative. 3x squared plus 0. We don't need to write the plus 0. And that's it, right? So this is our formula we found for f prime of x. So let's move on to the derivative of cosine. So you can use the exact same methods we learned for finding the derivative of sine. So we're not going to go through it again. I'll just tell you the result. It turns out the derivative of cosine x is equal to the negative sine of x. So it's important to remember that negative sign. Now let's go to the derivative of tangent x. So for this one, we're going to find the derivative of tangent. We're going to start by rewriting tangent as sine over cosine before we take the derivative. So now you can see this is the derivative of a quotient. So we can use the quotient rule. So over here we have the result, the original denominator squared. And then in the numerator, we remember the rule, bottom times derivative of the top minus top times derivative of the bottom. In the next step, we calculate these two derivatives. So we just learned the derivative of sine is cosine, and that the derivative of cosine is negative sine. The rest is just simplification. So this is cosine squared, minus times minus is plus sine squared. And then in the numerator, we have that identity we're all familiar with. Cosine squared plus sine squared we know is equal to 1. So we end up with 1 over cosine squared. And if you remember the identity, secant is equal to 1 over cosine. And because it's squared, that means this is secant squared. So we just found that the derivative of tangent x is equal to secant squared of x. And so here's our conclusion for the derivative of the tangent function. So far we've found the derivative of 3 of the 6 trig functions. We did sine, cosine, and tangent. There's still 3 more to go. Now these 3 can be derived in exactly the way we did with tangent. On the previous slide we rewrote tangent in terms of sine and cosine and then used the quotient rule. You can do the exact same thing to get these other 3. So we're not going to take the time to go through those in class. I'll just summarize the results. So you can see derivative of cosecant is equal to negative cosecant x times cotangent x. The derivative of secant x is equal to secant x times tangent x. And the derivative of cotangent x is equal to the negative cosecant squared of x. Okay, so these are the results. We now know formulas for the derivatives of all 6 trig functions. And keep in mind these formulas are only valid if you're considering x being in radians, not degrees. Here we're asked to find some derivatives. So in number 1, the first thing you should notice is this is a quotient of 2 functions of x. So we need to use the quotient rule. That's our starting point. Then we'll likely have to use some other rules within that. All right, so here y is a function of x, so our notation for the derivative would be dy dx. Now for the quotient rule, we take the original denominator and we square it. Now in the numerator, remember our formula, you take bottom times derivative of the top minus top times derivative of the bottom. Okay, next simplification, we'll take those 2 derivatives. So we have x cubed times the derivative of cosine we learned is negative sine. And then copy the minus cosine. And then using the power rule, the derivative of x cubed is 3x squared. And the denominator here is a simple simplification. When you have x raised to a power raised to another power, you multiply the exponents. So that's x to the 6th. And I'll do one simplification here to make, there's a pretty easy simplification to make this look nicer. So negative x cubed sine x, that looks better than the way it was written before. And then on the next term, it looks better to put everything in front of the trig function. So minus 3x squared cosine x. And that's our dy dx for number 1. Okay, let's go to number 2. So here z is a function of t, so the notation for the derivative is dz dt. Now this one we have a difference. Those are much easier than products and quotients because you can just take the derivative of each term individually. So we start with the derivative of 3t squared, so that's just a simple power rule. We get 6t. Then we have minus 4, right? When you're multiplying by a constant, you just carry along that constant in the derivative. Now we need the derivative of secant. So if you check that one from our formulas, you'll see the derivative of secant is secant times tangent. And here, because they're t instead of x, make sure you keep those as t's. And that's about as far as that one will simplify. Okay, so again, you can see sums are pretty easy compared to products and quotients. So you just need to be able to do this type of derivative calculation for involving any of the 6 trig functions. So you'll want to start committing those formulas to memory. This example shows us an application of using these derivatives of the trig functions in a case of simple harmonic motion, right? You might have heard that term. Simple harmonic motion is referring to an object that's oscillating, and its oscillation can be described by a sine or cosine wave. So in this case, the object that's oscillating is attached to a vertical spring. Its rest position is here, so if the system here were at rest, this mass here would be at position 0. But then it's stretched, someone stretches it down to 4 units beyond the rest position and releases it, and it starts oscillating up and down. And the function that tells its position as a function of time is s, which is the position, equals 4 cosine t. So it's just going to oscillate between, right, that has amplitude 4, so it's going to oscillate between 4 and negative 4. So the question here is to find the velocity and acceleration. So we've already learned that to find velocity, if you know the position, you just take the derivative of position, that gives you velocity. And then to find acceleration, we need a second derivative of position. So this is just a matter of computing the first and second derivatives of the given function. Our position function, we can see at the top, this was given to us, s equals 4 cosine t. So to find velocity, we just need to take the derivative of our position function, and since it's a function of t, the notation is ds dt. So here we've just plugged in the formula for s. We're taking that derivative, so this is a simple one. You can pull the constant out in front or just carry it along. And then the derivative of cosine t we learned is negative sine t. So we just arrived at our velocity function equal to negative 4 sine t. Now to get acceleration, we know that's the second derivative of position, but that can be thought of as the first derivative of velocity. So we need derivative of velocity, so we plug in our velocity function that we just found. We want the derivative of that. You can pull the negative 4 out in front, or just carry it along, and then find the derivative of sine t, which we learned is equal to cosine t. So now we have our formula for our acceleration function, negative 4 cosine t. So far in Chapter 3, we've learned several shortcuts for taking derivatives of certain types of functions, but there are a lot of functions that are more complicated, and those rules won't work on those more complicated functions. And usually those have the form of composite functions, right? If you remember composition of functions from pre-calculus. So in this section, we're going to learn a rule called the chain rule, and it tells us how to take the derivative of composite functions. This function is an example of what I was just talking about. This function, the square root of x squared plus 1. This is too complicated to use for any of our previous rules to handle. Right? You could try writing the square root as a 1/2 power. If it were just x to the 1/2 power, we could use the power rule. But the thing under the square root is more complicated than just x, so the power rule wouldn't apply to that. So when we realize this is a composition of functions, we're going to develop a new rule that will let us take derivatives of that type of function. So here, let's verify that it's a composite function. So remember, with composition of functions, you have an inside function and an outside function. The inside function is pretty easy to see here. It's the expression under the square root, x squared plus 1. So we're going to define u to be that inside function. So let me label that. Now the outside function is the one that's doing something to the inside function. So here, the question is, what are we doing to x squared plus 1? Well, we're taking the square root of it. So the outside function is the square root function. And so if u represents the inside, right, u is the x squared plus 1, the outer function is the square root of u. Okay, so let's label this one as being the outside. Okay, and now think about what happens, just to verify this, when you compose f with g, right? You've seen this notation, f circle g means this, f of g of x. So just to remind you of that notation, when you see f circle g of x, that is defined as f evaluated at g of x, right? And that's what we mean by a composition of functions. Review from pre-calculus. So now just check that when you compose together these two functions we defined here, that it does give you the original capital F function. So f of g of x. If you remember working with these in pre-calculus, you always start on the inside. So replace g of x with its formula, which we defined to be x squared plus 1. And now what this tells me to do is go to the formula for f, which you can see it's up here. And I'm going to substitute in x squared plus 1 in place of the variable u. So over here it's the square root of, x, and then replace that u with x squared plus 1. And notice that's exactly the original function that was called capital F. Okay, so first, this was just review of pre-calculus, just to realize the given function here is a composition of functions, and to be able to identify the inside function, in this case was x squared plus 1, and the outside function was the square root of the inside function, so the square root function. So these two functions we found, f and g, those are simpler functions, and our rules that we've already learned will let us take the derivatives of those functions. So now the question is, how can we do that? If we want to find the derivative of this composite function, is it just going to be derivative of f times derivative of g or something like that? That's what we want to determine next. If you recall from the previous slide, we started out by being given y as a function of x. We called it capital F of x. And we recognize that as being a composite function. And so we defined the inside part to be u as a function of x. We called it g of x. And then the outside function, we called that y equals a function of u. That was the square root of u function in our previous slide. So we have three functions we're looking at. So there's three corresponding derivatives. From this function, the derivative would be dy dx. From this one, it would be du dx. And from this one, it would be dy du. Okay, we can view all of those as rates of change. Right, this would be the rate of change with u with respect to x, rate of change of y with respect to u, and rate of change of y with respect to x. So just taking an example, suppose u changes twice as fast as x. So that means the rate of change of u with respect to x would be 2. And assume that y changes 3 times as fast as u. So that means dy du would be 3. So now the question is, what is dy dx from the original function? Well, putting all this together, right? If u changes twice as fast as x, and y changes 3 times as fast as u, we have this chain going, right? Y depends on u depends on x. And so we said we're assuming u changes twice as fast as x, y changes 3 times as fast as u. How fast does y change with respect to x? So it makes sense to multiply those, and you would get 6 times as fast. So intuitively, the rate of change of y with respect to x would be the product of these other two rates. So using the analysis we just made, we conclude the chain rule that tells us how to take the derivative of a composite function, f composed with g. So the derivative of this function would be the product of the derivatives of the two functions here. So it's f prime times g prime. Right, those are the other two rates we talked about from the previous slide. Now there's something we have to be careful about, and that is what is the input to each one of these. So you take the out, right, f is the outer function, g is the inner function. It's the derivative of the outer function, but it's not x plugged in, it's g of x plugged in. So that's the derivative of the outer function. And then multiplied by the derivative of g, and g is the inner function. Right, so the big picture is derivative of outer function times derivative of inner function. What you have to be careful about is for the outer function, you don't plug in x, you plug in the g of x, where g of x is the inner function. Now the Leibniz notation I think is much easier to remember. So when you think about the chain rule, we often think about it in this notation. So dy dx represents capital F prime, right? Because here y was a function of x, so dy dx. This is the derivative of the outer function. So the outer was y as a function of u, so that derivative is dy du. And then the inner function was u as a function of x, so the derivative in Leibniz notation is du dx. And the reason why this is easy to remember is on the left we have dy dx. Notice on the right there's the dy and the dx, so it looks like we just multiplied and divided by du. That makes it really easy to remember. Now we didn't really multiply and divide by du because these are notations. This fraction is not really talking about division. It's a notation for a derivative. Same with these other two notations. But thinking of it that way, multiplying and dividing by du, is just a helpful way to remember this formula. In this example, we're going back to this function we presented at the beginning of the section that we said our previous rules don't work. Right? If this were just square root of x, we could write it as x to the 1/2 and use the power rule, but this is more complicated than that. The power rule doesn't apply if you have some complicated expression raised to the 1/2. So we already recognized that this is a composite function, so I always start with the inner part. So if we define u to be the inside part, okay, and so here this is u, and we've called it g of x here. So that's the part inside the square root. And then if that's u, the outer function would be the square root of u. So that's our outer function. So that's always the important starting part, is to be able to identify the inside and outside functions that make up this composite function. Now we're going to solve this using two methods. First, we're going to use the prime notation for the chain rule, and then after we finish this, we'll use the Leibniz version so you can see how it works in both versions. So we need the derivative of both functions, right? So let's start. This is our definition of f. We need f prime. So if you rewrite that as u to the 1/2, you can just use the power rule. You bring the 1/2 down in front, reduce the power by 1. The new power is negative 1/2. And then if you wanted to simplify this, the negative exponent means you can put it down in the denominator and write it as u to the positive 1/2, and then we've just converted that back to a square root, but now it's in the denominator. We also need the derivative of g, so that's a simple one, right? 2x to the first power plus 0, so it's just 2x. Now here we've just copied the chain rule, and we start with f prime, which we calculated here, but it's not f prime of u, it's f prime of g of x. Now what was g of x? X squared plus 1. Okay, so let me write out a little bit more here. So this f prime of g of x is what we're working on. We can replace g of x with the formula, which is x squared plus 1. Now what this tells me to do is to go to the formula for f, right? So f of u is the square root of u, and wherever I see a u, replace it with x squared plus 1. So that, oh sorry, I said that wrong. This is f prime, not f. So we go to the formula for f prime, which is here, and now we make the substitution. Wherever we see a u, replace it with x squared plus 1. So it will be 1 over 2 square root of x squared plus 1. Okay, so that's just a little bit of extra work showing where this came from. Then we multiply by g prime of x, which we already found is 2x. And then the 2's cancel, and we get this for the final formula for our derivative. Okay, so basically we identified this as a composite function. Then we figured out what the inside function formula was and what the outside function formula was. We computed the derivatives of those two, found f prime and g prime, and then we multiplied them, right? F prime times g prime. The extra thing you need to remember, though, is when you write f prime, you need to replace the u back in terms of x. So up here is where we define u in terms of x. So we substitute that in, and then we get our answer in terms of x. Now we're going to go through the same example, but this time we're going to use the Leibniz form of the chain rule, which I've copied up here. So we've already done part of the work. We identified our inside function and our outside function. That was the same as last time. The only difference is we're not calling them f of x and g of x. We're just saying let u equal the formula for the inside and let y be the square root of u would be the outside. Now you can see from the formula for the chain rule in the top right that we need two things. We need dy du and we need du dx. So to get dy du, look at your formula for y as a function of u. You can rewrite that as u to the 1/2 and then use the power rule to find that derivative. So bring the 1/2 down in front, reduce the power by 1, so now the power is negative 1/2. And we saw this before. You can rewrite that as 1 over 2 square root of u. Now we need du dx. So look at your formula for u as a function of x. Take the derivative, you get 2x plus 0. So those are the pieces we need. So now let's put them all together. So to get dy dx, which in prime notation is capital F prime of x, will be the product of these two derivatives. So dy du, we just found that over here. Du dx, we found that over here to be 2x. Now we can't leave a u there, right? That's not part of the, that was not one of the variables in the original function. So we need to back substitute for u, replace it with x squared plus 1, and then we just simplify by canceling the 2's. So we got the same result using this version. So either way you want to think about it is fine, the prime notation version or the Leibniz notation. Now that we've gone through an example in full detail, let's do one where we sort of simplify the way we think about it. We'll be following the same steps, just making it a little simpler. So first recognize that you have a composite function here. If this were just e to the x, we would know the derivative. We have a rule for that. But this is e to the some other expression that's more complicated than just x. So you have to realize this is a composite function because we've replaced that x and the exponent with some other function. So we need to identify the inner and outer functions. So starting with inner, we've been calling that u. That's the exponent here. Right? It's the part that if it were just plain x, it would be easy, right? That's where your inner function is. And then the outer function, to get that, just rewrite the given function, y equals e to the power, but then replace that power with what we call u. Okay, so now we have our inner and outer functions. Each of those, we can find the derivative of each of those. So then here we have u as a function of x, so the derivative would be du dx. And that's an easy one. 3 times 1 minus 0 is just 3. And then the second one, this is y as a function of u. So when you take the derivative of that, it would be dy du. And so the derivative of e to just a variable u is just itself. Right, because the rule for the derivative of the exponential applies here because it's e to just a single variable. There's no other complicated expression in the exponent. So now, going back to our original function, as it's given, y is a function of x. So finding the derivative of this means finding dy dx. Notice over here we have dy du, but that's not what we need. We need dy dx. So here's the dy dx, that's what we're trying to find. Now just copy the chain rule, right? You keep the dy and the dx like this, and then multiply and divide by du is how we think about it to help remember that formula. But those are the two derivatives we just found at the top right, right? The dy du, we found that to be e to the u, and the du dx, we found that to be 3. So this is, you could write it as 3e to the u, but we always need to back substitute, right? There were no u's in the original problem. So we replace u with what we did, how we defined it. Right? If you look up where I wrote inner function, u is the same as 3x minus 5. And that is our derivative here. So we'll do a lot more practice with these next time. we're out of time for today, so we at least saw an introduction to the chain rule and a few simple problems where we used it. But this is the type of method that requires a lot of practice, so we'll do a lot with this at the beginning of our next lecture. Let's summarize what we covered today. We covered parts of 3 sections. Section 3.2 on the product quotient rules. We had started that last time. We covered the product rule last time. And today we learned the quotient rule. So that tells us, of course, how to take the derivative of a quotient. We did all of section 3.3 today on derivatives of the trig functions. So we learned formulas for the derivatives of all 6 of the trig functions. We also did some examples where we saw we could combine these rules with some of the rules we had learned earlier. And then we started section 3.4 on the chain rule. And we learned this rule, and it tells us how to take the derivative of a composite function. So we did some examples here, but we'll do several more examples next time just to get some extra practice with the chain rule.